Hello and welcome. I am Dr. Leslie Sluss with the Clean Coal Centre, and today I will be giving you an overview of my latest report, which we hope will be published within the next week or so, which looks at blending of coals to meet power stations' requirements. Now, if you're watching and listening to this live, good morning or good afternoon, please feel free to type an answer in, or a question, would be better, in the box at the bottom there, and I will try to answer that at the end of the presentation. If you're not listening to this live, if you're listening on catch-up, then you can use my email address, which will be on the last slide, and I will be more than happy to reply as best I can to you. Now, the reason I'm going to look at coal blending is to try and explain it from the viewpoint of a utility manager. Now, if you talk to anyone in the industry, there tend to be comments about how coal is sold as cheaply as possible. People will sell you a mixture of the lowest quality of coal available to them so that they can make a maximum amount of profit. And while that is true, that is looking at it from a coal mine manager's point of view. I really want to look at looking at it from a utility operator's point of view, to maximising the blend, yes, at lowest cost, but making sure that the coal plant operates as it should. And so to do this, we're looking at why coals are blended, the chemistry of the blending, which as far as I can see is very much a dark art to some extent, and then looking at the techniques that are used in practice. And then hopefully we'll have some time for some pretty pictures of what people are actually doing out there, as there's some pretty amazing equipment being sold. Now, the reasons for coal blending, obviously the priority is cost. The fundamental aim of any power plant is going to be to produce power at the lowest possible cost. And coals vary in quality, with lower quality coals being cheaper. And so it's a plant operator's job to buy the most cost-effective coal he can buy, whilst keeping the plant performing as it should. Now, this picture shows the flow of traded coal internationally for 2002 and predicted for 2030. I'm not going to go into this in any detail at all. It's really here just to show how much travelling coal can do, that any operator of a plant almost anywhere in the world can be buying coal from almost anywhere else in the world. And as coal demand continues, new mines are being opened up and new infrastructure is created to make sure that coal available into the international market. And so coal users now have significantly more opportunity to pick and choose which coals they want. And blending allows plants to take advantage of the different coals available to them. Many plants we see operating in Southeast Asia, for example, can take up to 100 different coal types and can blend each of these as required. Although the choice of coal may be increasing globally, there are many instances where a coal plant has been designed to burn a specific coal, and quite commonly this would be an indigenous coal. Many plants are built next to coal mines, and that is the coal they will use for as long as possible. But of course that coal may run out, or the quality may vary as the mine goes deeper, and so coal blending, by adding a little bit of coal from somewhere else, can extend the life of this local supply of coal by diluting it with imported coals. At the opposite end of the spectrum, we have areas which rely heavily on imported coals and don't really have any indigenous coals to pick up on. And these areas will have stockpiling as a priority to ensure that their supplies are kept adequate. For example, the Taiwanese government requires that the country hold 1/3 of the total national annual demand of coal as a safety reserve. So at any time, Taiwan has 1/3 of the coal that they will need for that year sitting there doing nothing. And at the same time, the government requires that that coal be coming from different and diverse sources, so that they are never overly reliant on any individual source of coal and are never potentially held to ransom economically or politically and so on. And this avoids situations where there may be a crisis created by ensuring that the coal supply and demand is always there. So moving on, let's look at why individual plant managers are interested in coal blending. Now, plant operators know what suits their plant. Their plant has been designed to burn a specific coal, and therefore they're going to select the coal that meets the minimum performance requirements of their plants. And when the specification cannot be met with the coals available to them, they're going to have to make a decision as to which parameters matter the most. Are they most concerned about the ash or the sulphur and so on? And then they will look at the blends available to them and buy sort of to maximise as many of the parameters as they can all at once. As I said, coal plants are designed to suit to burn the coal available to them. However, that may change. The coal mine may run out, and this means that they have to adjust to ensure that their plant continues to operate in the way that it hasn't done in the past. Because if you change your coal, then the plant operation will also change. Excuse me, you will get a change in combustion efficiency, you will get plant performance issues and specific issues such as slagging and fouling and messing up of your plant, which can be extremely expensive to remedy. Major coal characteristics which are regarded as most important tend to be things like ash or sulphur content, and the coals will be bought according to that. And however, it's been noted that coal quality is important, but the consistency of that coal quality can actually be more important than the quality itself, and I'll have to explain what I mean by that. If you have a coal that meets specifications, then that's good, but if it varies throughout the coal so that you have regions in that coal pile which is high sulphur or high calorific value, then the way it burns will not be consistent as that coal is fed into the boiler, and you will get older units what they call hunting, which is fluctuating in pressure when coals are not homogeneous or fully mixed. And this can happen when there's even only a 1 to 2% variation in the coal characteristics of the coal mix. And so many plants will actually prioritise according to homogeneity of the supply rather than the characteristics of the supply to some extent. And so some plant operators will find a blend that suits them, and for as much as possible they will stick to that blend and they will just kind of reorder on a direct debit basis, and that suits them. However, you have other plants who like to mix it up a bit, change the blend every day, maximise their performance and keep their costs down. And to some extent the latter approach is actually becoming more common. However, for many units, it's not their decision. It will depend what's available to them, and in many situations they're being run out of a head office where the coal is kind of sent to them and they don't really get much of a choice as what's coming at them. Now, there are other reasons for coal blending which are new, and so plants are facing new challenges. Pollution control requirements are changing. If you've read any of my other reports, we know that SOx and NOx and particulate emissions are tightening over time, and new requirements are coming in with respect to mercury emissions and even CO2 emissions. And so plants are going to have to consider the coals they're burning, not just to make sure that the plant burns properly, but also to make sure that they comply with emission requirements. There's actually a project in Greece to perform selective mining of indigenous lignite, which combined with the blending and drying of the lignite could actually improve plant performance to reduce emissions, including CO2, so that the plant efficiency would go up. And that looks like a very interesting project to follow. Another example is the USA. It's been trading sulphur emissions under the Clean Air Act for years, and much of this sulphur has been achieved at very low cost through the use of low sulphur coals. It's been an extremely effective way of reducing emissions over there. However, some of these low sulphur coals, such as the Powder River Basin coals, are lower heating value and higher friability, and so switching the coals is not as simple as some plants would wish. They may wish to just fire PRBs, but they can't because they get slagging or fouling, or the plants just don't work. And so blending can help reduce the variation in some of the coal characteristics while allowing the overall sulphur content to be reduced. More and more we're hearing about nitrogen emissions also. And some people are a little bit confused by that because, of course, nitrogen emissions from a coal-fired power plant come not only from the nitrogen in the coal, but the nitrogen in the combustion air, which can be controlled by the way you fire and the low NOx burners and so on. However, some of the US states actually have seasonal limits for NOx emissions, especially those down the East Coast, where during the summer months where there's more problem with ozone and volatile organic compounds at ground level, they have to reduce the NOx emission limits are actually lower than they are in the winter. And so rather than invest in control technologies, low NOx burners and selective catalytic reduction systems, it actually makes sense for them to buy lower nitrogen coals during these summer months. And in future, as people who know me know, mercury is an issue of concern. The new UN Minamata Convention will have an effect on mercury emissions from coal-fired power plants within the next 5 to 10 years, I would predict. And blending of coals to reduce mercury emissions will actually be a really good and a really cost-effective way of reducing mercury emissions in many regions, not just by buying lower mercury coals, but by mixing coals with higher chlorine. You will actually get a huge mercury reduction virtually free of charge. And so coal blending could become more important in the future as time goes on. Now, each plant has individual challenges. The reason one plant will burn a certain coal is different from the reason why another plant will do it. As I've mentioned, governments such as that in Taiwan are worried about the coal supply to them, and so they will require that coal comes from different regions of the world to ensure energy security. Other regions will be trying to make the most of the indigenous coals they have available to them because they are the cheapest available options. And they will be extending the lifetime of that coal by blending from outside. The markets always vary, and they always will vary in terms of cost and availability. And so, although the plants are designed to fire specific coals, they can make changes without causing damage to the plant if they do the blending in a sensible and appropriate manner. And they can also do this blending and forming in such a way that they can be complying with emission challenges at perhaps lower cost than they might have to do by putting on retrofit control technologies. Now let's move on to the more nitty-gritty of the coal blending, how it's actually done and how it's controlled. Now, coal blending is only going to be successful if you know what you're blending and how you've blended it, and so sampling and analysis systems are integral to the whole thing. I'm going to talk about how this happens in practice and how samples are taken and how the data are used to control the final blend of the coal and how information is provided into the blending systems and into the models that are used. Now, sampling analysis is required at several stages through the supply chain. The mine itself is going to have a good idea of which areas of the mine are producing the nice, good quality coals and which areas are producing perhaps slightly dodgier, sketchier coals that can be blended to some extent in with the nicer coals to give an overall acceptable quality coal. And so the analysis is going to be going on all the time at the coal mine, and that information is arguably available to those buying the coal from that site. When blending then occurs, that information will be fed in so that you can calculate how much you want to put in the mix. But of course, you will then want to reanalyze the mix to make sure that you're actually getting what you're planning to get with your blend. And at the end of the chain, once the blending has occurred, whether it happens automated or with a big bulldozer, your final user is going to want to guarantee that what you've told them is in the blend is actually what is in the blend. And this will be achieved usually with a manual method, although automatic measurements may have happened through the coal chain. Usually the certificate that comes with the coal at the end is based on a manual sampling and analysis method, which complies with ISO, International Standards Organization, or US or BSI or European manual method reference methods that are legally determined to be the most appropriate to give the most exacting and comparable results. And in some cases, this information on the specifications of the coal are actually used to predict the emissions. So plants, for example, as we've talked about in the USA, buying low nitrogen coals to comply with the emission limits will often use the data provided by the coal supplier to estimate what their NOx emissions are going to be. And obviously there will be an issue if this is not the case. Now, obtaining a representative sample of coal for analysis is a significant challenge because coal piles, seams and everything, where you look at a pile of coal, one lump of coal is going to differ from the next lump of coal. And in fact, even if you crushed up that coal, different regions of that individual coal lump would vary because it's simply not homogeneous. That's not the way coal is created. And so obtaining a representative sample is going to be a challenge. You can take a grab sample and you can assume that that's going to represent the whole pile. And then you take that grab sample and you're analysing using the ISO, that's the International Standards Organization, or the CEN, which is the Comité Européen de Normalisation, which is European Standards Methods. And these are the ones that are used. And There are online sampling systems, such as this little guy shown here, which is a true belt sampler, which tries to kind of move a conveyor belt of coal along and will try to randomise the sampling process to make sure that the sample taken is most representative of the whole stockpile, as it were. But again, you're never going to get a true feed of what is happening because coal is just simply not homogeneous. Now, as coal sampling can happen throughout the coal chain, so can coal blending. There will be a certain amount of mixing, not necessarily blending, which occurs at the mine as they take coal from the individual seams. They will move it into one big pile and they will try, as I say, to mix perhaps a little bit of lower quality coal with some higher quality coal so that the general output of the mine is what they say the quality is. Now, blending can also occur during the transport stage. Lots of different coals can be dropped into rail cars or into ships or trucks, and as these coals are moved from pile to pile into truck or whatever, mixing is going to occur as that happens. More specific blending can then occur downstream at a dedicated blending plant, either say at a port or a large processing site, or even at the coal-fired power plant itself if there is space. However, it should be remembered that coal is expensive to move. Every time you pick up a pile of coal and put it down, it's costing you time and money. You're either paying a bulldoze manager to do this, or you're paying for equipment which does this. And so therefore, people don't want to move coal if they don't have to. And if they're going to move it, then if they can integrate the blending with the movement, then this is going to save an awful lot of time and money. Moving on to the more intricate chemistry of the blending, and as I mentioned at the beginning, it is a bit of a dark art because some of the coal characteristics are going to behave like you want them to and some are not. And this is what's called an additive or non-additive effect. And so we have some parameters that behave properly and some that do not. For example, the elemental content of the coals. You know the carbon content or the chlorine content or the sulphur content of your coal, or each of your coals, and according to how much of each of the coals you put into the blend, you can calculate fairly accurately what the final overall average characteristics of the blend are going to be. And that's nice, that's an additive effect. You also have, unfortunately, non-additive effects such as the grindability and swelling and so on, and the combination of two coals will not behave as a combination that you would expect or you could mathematically predict. And to some extent we have some areas where it's unsure, so that in some cases it will be additive and in some cases it's not, and you basically have to work out what's going to happen, prepare a complicated model, or perhaps more sensibly test the blend and see what's actually come out in the long run as the actual final result. If you type coal blending into Google, which I've done many times over the last couple of months, you will get sort of things like this, which are free online calculators. However, what you see here is that the parameters calculated by the blending system here are those ones which are largely additive. So all this is really doing for you is letting you put in the data for your two coals, the blend ratio, and just doing the math for you. Largely you could have done this on the back of a piece of paper yourself if you wanted to. There are more complex models available if you're willing to spend a bit of time and money. There's a significant amount of work being published, especially in China. If you do, like I did, and go into Scopus or any other search engine and type in coal blending models, there are thousands, literally thousands of coal blending models being developed, largely in China, which gives an indication of just how complex coal blending can be when you're talking about non-additive parameters, but also just how important it is. People wouldn't be investing in these projects if they didn't really want to be able to blend the coal. There's obviously a lot of money in coal blending and plant performance optimization. And so some plants will invest a lot of time and money in maximizing the optimization of the coal blend. Other plants will have well-established routines and will stick to the norm and will make very little variation. And to some extent they will achieve their blending, as I say, with a quick calculation and a bulldozer. I must point out at this point that the report does tend to focus on the more advanced techniques, as these are what you find if you search through the published literature because they're interesting and they're new and they're challenging. But I must emphasise that the methods I'm talking about in the report are not necessarily the norm. yes, there are a lot of exciting models and blending tools and expensive equipment, but you are more likely at the moment to see a plant with a bulldozer and 2 piles of coal next to it achieving blending than you're likely to see a plant with a huge, big, expensive dedicated blending system. However, times are changing and dedicated blending systems are coming into their own at this stage. Now, this is an example of a coal blending management plan. I've got a few slides which show what's going on and just how complicated these systems can be. This is this chart showing the steps in the blending software used at the Shinta plant in Taiwan. It's a very, very simplified summary of a ridiculously complicated goal programming model that they use at the plant in order to determine the optimal quantities of coal from different stockpiles to be blended to meet environmental and boiler performance requirements. So what they've done is put into the model what they need the plant to have in terms of ash content, sulphur and so on, what they have to achieve in terms of emissions and so on, so that they know what parameters they need in the coals. And then at the other end of the models, they're putting in what coals are actually coming into them through the different suppliers. Now they have 15 different suppliers providing coals that fall into around 4 to 6 different grades, which then need to be blended to meet the 4 different boiler parameters. So as the coal is delivered, it comes with the information on its characteristics, and the model will then say, okay, put that coal from that truck there in that stockpile there. And the stockpiles will be coordinated accordingly to ensure that the blending is what it needs to be. Now, these models and programs are available and can be useful for large plants, and even more so if you're talking about a centralised stockpiling area. This plant's providing coals for 4 different units, but a stockpiling area providing blends for hundreds of different plants would obviously be extremely cost effective. Many plant operators will never see a blending computer in the model and instead work with their bulldozers and their piles. However, the future is what you're seeing in front of you when we're talking about moving towards more specific blending to meet requirements. However, in any of these situations, your model is never going to be perfect, and so you will never see anybody putting a new coal blend into a coal-fired power plant and expecting it to work. You're going to get predictions. You're going to do small-scale burns, potentially in a lab, and then you're going to move up to a test blend in your full-scale plant. And in some cases, you'll talk about sort of phasing this in slowly so that you'll maybe add 1, 2, 5, 6% of the new coal, see how it works in practice, and if something goes horribly wrong, then you obviously stop immediately to make sure that you're not causing damage. So let's look at how you physically mix and blend those coals. As I mentioned a moment ago, moving coal is jolly expensive and it adds to time and cost, and it therefore makes sense to have the blending happening as you move the coal. So coal coming into a stockyard can be blended as it arrives. You pile it into stockpiles with other coals. So rather than piling your high sulphur coal in one corner, low sulphur coal in another, you pile them together, but you do so in a coordinated way. Strategically, as shown, for example, in the top left there, different arrangements for laying out different coals being piled basically into a big pile of coal. But you create different areas or regions within the pile which contain the different coal characteristics that you want. And then you can go and specifically create a slice or take out a wedge, knowing that within that wedge you've got a combination of layers that together will give you the blend that you want. And so different blends can be attained by different cuts through the same coal pile. And it's maybe in the worst case scenario, you could even recover individual coals back from the stockpile if you needed to. Now the stockpile is like one of these before piles in a cookery show. It shows you ingredients but nothing has happened. The actual mixing is achieved during the reclamation method. Scoops or buckets or wheels or blades or anything that can grab the coal will take sections through these coal piles as required. And normally these will include some sort of vibrator or shaker so that the coal is mixed as it is dragged through the slice taken from the pile. Now this is quite a simple approach. Down the bottom we have an extreme advanced method used at a cement plant, so it's not a coal plant, it's a cement plant in Kalimantan, Indonesia, where the blending is achieved in such a complete and controlled way that it's actually homogenizing the coal, and the coal blend is consistent throughout. So they take the different coals and they create this even layers across a flat surface. They collect through the different layers and they homogenize, grind and blend as they're doing it. So here, I believe, is a better picture. That is the Kalimantan processing system in the top there, where that cutter is taking slices through the different layers of coal, grinding, homogenizing, and creating basically the ultimate blend, a super homogenized coal. But obviously equipment like that is not cheap, and it's not something you wouldn't do if you weren't providing a huge amount of homogenized coal to specific requirements to someone who is willing to pay for it. And again, down the bottom there, we have just a reminder of what happens at a lot of other plants. A nice little bulldozer and a couple of big piles of coal. Now, if you don't have room for stockpiles, you can always go with silos, which are rather fun because they can store more horizontally, so they take up less space in a stockpile. And they can also keep the coal away from environmental and weather conditions, and so on. Keeps your plant tidier as well, I suspect. And so coal will be fed into each of these silos according to characteristics, and then the hopper at the bottom can be used to release individual coals from the different silos. Now, if you do that onto a bed or into a truck, then obviously the rate of feed of the different coals from different silos will give you a blend. An online analysis, sampling analysis as the blend is created, can create a specific mix to highly specified requirements. Here we see an example of an extremely complex system, which is working from everything from the shoveling and the excavation of the coal, analysing and noting down what's happening each stage of that process, through the trucking, what's coming in each truck, what you're storing in each hopper and different bin, the blending that's going on, what's finally being fed into the different silos, which themselves may be blended or which can be then blended further, and then the output to the final customer. So although this is obviously complex, we can imagine that at the end of the process, once this is established, this is an extremely nice way of getting from the coal coming in from your mine through to the exacting requirements required by your customer. And this is the same kind of system, looking at it from a fleet manager's point of view, where he's going to be looking at which truck is moving where, what's being fed into each hopper or silo, and what is going out in the truck to the final end user. Everything controlled and analysed in real time, and a little bit of investment at the beginning ends up with something that produces extremely high quality, high saleable coal to user specific requirements. Another one, an example of data handling when you're talking about the different sensories coming in. So you've got real-time data coming in from your coal blend, from your silos, from online analysis systems to ensure that the blending goes on in a real-time way, and that the system is always aware of what is happening. There's a feedback loop to ensure that the control is there to ensure specifications are maintained. Now, what is used obviously varies by what is needed. I've shown you some examples there of extremely complex and costly systems, but what people need will vary on a case-by-case basis. Space available. Do plants have space for blending, and do they need to blend on site? It's taking a lot of your space available around in your land. It's difficult to maintain, and you're going to need material and equipment and staff to actually run that, and that's going to cost you money. It might be cheaper just to get a blend delivered, but then you're adding cost in terms of delivery, and you're going to have to pay for blending because obviously someone else has gone through the bother of analysing, blending the coals to what you require, and they're going to require reimbursed for that. It depends on the complexity of the mix as well. If you have a simple mix of a high sulphur coal and a low sulphur coal, then perhaps you can do that with a bulldozer and 2 piles of coal. But in some situations, if you need a complex blend, then you are going to spend an awful lot of money to get that. And in some cases, such as the US, where the emission standards vary seasonally, we were talking about the NOx limits there, Plants will actually vary the coals they buy from season to season, and so may have to have access to stockpiles of different coals through the season depending on the emission requirement at different eventualities. It's all very site specific. I don't have time to give examples here, but hopefully you'll take time to look at the report and you can see that I've got some nice pretty pictures of what different people are doing where, and there's some great case studies. For example, this is a particular favourite. This is the Lig blending plant in China built by Petrocom Energy, and I've chosen to put it up here because it just simply blows my mind how big this thing is. It's designed to blend 10 megatons per year of coal. So you've got 6 silos, each holding 9 kilotons of coal, so that's 54 kilotons, and it can produce a simultaneous blend of up to these six coals at any one time at a rate of 4 to 6 kilotons per hour. And that can be in either direction, so you could be blending and feeding and then popping this on a ship, or you could be sending it to storage, or you could be sticking it in one of these 1.5 kilometre feeder belts, which will take it to the plant or to the stockpile or wherever it needs to go. This thing is huge. Feed rates between 160 and 1,600 tonnes per hour, and if the blend varies by more than 1%, they can switch. It can feed back and say that blend's not where it needs to be, and it can change and adjust the blend, correcting it within less than a minute. So we're talking about extreme online analysis and extreme blending here to meet customer requirements. Obviously, this is not something you would see at an individual coal plant. This is at a dock where shipments are coming in from around the world, and a blend is being created that will be suitable for many plants. And this is something that's happening in China. We expect several plants of this scale to be built over the next years to act as a centralised coordination blending area to provide coals to different plants. This should reduce both costs and emissions. By centralising processing the coal, then you know that you're delivering cleaner coal to specifications to each of the plants, and you're doing so on one truck from this source, as opposed to a plant blending, receiving perhaps 6 trucks of different coals and having to blend on site. This is so much more efficient and so much more effective in terms of the economy of scale. And so this is what we would expect to see happening more and more in China and India when we know coal use is going to go up and we know they're going to start complying with environmental challenges and efficiency targets. And it's great to see this happening. I'm quite excited about that. And so to sum up what I've been saying, blending is becoming more and more common because the coals available in the marketplace are changing. People are running out of the coals they're used to having, but there are more choices available to buy than ever before. But also coal plants are facing legislation and compliance issues that they haven't faced in the past. All of a sudden they have to reduce emissions and they have to increase efficiency, and this is not what the plant was designed to do at the beginning, and so they're having to face adjustments. They can either do this by retrofitting expensive control technologies, or to some extent they can achieve a little bit, perhaps more cost effectively, by adjusting the coals that they're burning. And so the challenge of any plant operator is to find a coal that's consistent, meets plant operating specifications, will meet emission limits, and which comes from a readily available and secure supplier and is as cheap as it possibly can be. And that's no mean feat. For some plants, blending on site will work fine, and it does work fine. For others, especially those which are part of a group of similar plants in reasonable proximity, a dedicated blending facility is possibly more appropriate. As I said, many countries such as China are going to be importing increasingly large quantities of coal, and dedicated coal blending plants such as the one I've just shown at ports or well-selected locations within each province could go a huge way to reducing the cost of supplying quality coals to the growing number of power plants. The Petrochem plant I showed is going to help not only plant performance but emission reduction, not just from the plants themselves but also from the transport sector. More coordinated movement of the coal means less emissions from all areas and not just the plant itself. So blending is a means for plants to optimise performance and keep costs down, but it's very plant and case specific. So please do read the report for more examples of the different systems that are in use today. The draft is available for those that are members, and the final report should be out by the end of the month, I expect, because I'm reading the final draft today. I will now move on and answer any questions that have come in. You are free to type them in at the bottom of the screen there for a few more minutes. I'll be available. Or if you're too shy or you're watching this on catch-up, then that's my email address on screen there, and I'm more than happy to reply to you as soon as I can. Okay, first question that's come up in is mercury additive? Would that it were, that would be wonderful. It would be nice and easy just to say we'll burn low mercury coals. It's not. In fact, the chlorine content of the coal is far more important with respect to mercury emissions, which surprises a lot of people. And this is actually one of the next question that's coming is, why do high chlorine coals reduce the mercury? I shouldn't be talking about mercury, but I will. Quick 2-minute guide to mercury. Mercury comes in two main forms, oxidized and elemental. Elemental's terrible. It goes straight through the plant. It's not sticky. It just does what it likes, and off it goes and contaminates the environment. Oxidized mercury is lovely and sticky and soluble. It'll stick to your fly ash and your unburnt carbon. It'll come out in your FGD and your wastewater. So we want oxidized mercury. And in the coal, a lot of mercury, the way it comes out depends on what's in the coal. If you have a high chlorine coal, your mercury gets oxidized through the combustion process. It's nice and sticky and it's captured. And so if you have a high mercury coal, then you would expect emissions of mercury to be high. However, if it's also high in chlorine, your emissions can actually be really low. And so mercury control can be achieved by blending high chlorine coals into the normal mix. And this is what is happening at many plants in America at the moment. And it's also something I expect to be seen used in India and China and other regions as a low-cost option for mercury control. It can be extremely effective. You can get 70, 80, 90% mercury capture by investing nothing, just by using existing control systems at the plant, if that mercury is oxidized, and that can be achieved in most cases with a higher chlorine coal. Obviously, a higher chlorine coal brings in its own issues, and it's not quite as simple as that. But if you type mercury into the internet, you will see many reports I've written on this, and I recommend you look at those. Am I aware that the sound is going off for about 10 seconds from time to time? No, I'm sorry. I'm hoping that's an issue with someone specific's internet and not with our system. Maybe if you try and play this back on catch-up later, it won't be quite so jumpy for you. Sorry about that. Surely coal blending is expensive. How can it be cost-effective? Good question. Yes, it can be expensive. If you're talking about that big plant we saw in China, then yes, that cost quite a few pence. However, over the long run, it should be cost-effective. It depends on how much you need to achieve. If your plant has extreme compliance issues and challenging coals available to you, then yes, it will be worth spending a little bit of time and money on getting a blend that is suitable to you. Another question, can coal blending models really predict how coals will behave in practice? Yes and no. Somewhat, yes, it will predict the emissions of sulphur and so on, but it won't predict the grindability and the combustion behaviour and the slagging fouling performance. It can't do that. The science simply isn't good enough yet. That's why if you type coal model blendings into the internet, you will get thousands of hits as people are working furiously to try and get the models better. The models are good, but my money is still on a power plant manager that knows his plants and knows his coal and is worth his weight in gold. He will be able to do back of the envelope calculation based on his expertise, which will probably give better results than some of the models that are out there. But hopefully over time the models will improve, and by testing rather than just assuming that the model works, then you're not going to make expensive mistakes when you switch blends. Let's have a look at this. Lots of questions coming in. Any idea how much cost blending adds to the dollars per ton of coal? No, I don't. I know that every time you pick up a ton of coal, it costs you another $1 or so. So yes, it's not cheap, but before that you invest in a blending technology or approach, you're going to work out how many times the coal is going to be lifted during that process, what machinery you're going to use, and whether the result is going to be cheaper than buying in a blend. There's always a simple calculation you can use to compare how much it would cost to do the blending yourself and how much it would cost to buy in the blend. And if you go to blending manufacturers, then I'm sure they'll be more happy to sit down with you and go through the cost options with you. I haven't really covered that in the report because it's always very hard to look at costs in a report that's going to be out there for several years, because these things change very quickly as the market changes. Another question: are there any countries where coal blending is more important and more relevant than others? I would say countries where you've got lots of coals coming in from different regions. So you're looking at areas like China, which are moving towards importing a lot more than they used to be. Blending is going to be hugely important over there. Blending could also be hugely and should be hugely important in India. As we know, they're burning low quality coals in many cases. Their plants are inefficient. Blending and coal washing potentially simultaneously could be an extremely good way of making their plants perform better and improving the quality of their coal in a single use. So I would hope to see it more there. And also, as coal supplies turn out in regions that used to have coals and things are changing, then yes, the coal markets are changing and coal blending will become more important in more and more places. Plants are getting older. They've been designed to burn a specific coal. That coal supply isn't going to last for 60 years. They're going to have to look towards blending to be able to maintain the coal quality that they're used to. Another question: any idea why grindability is not an additive property? Yes, it's all to do with the, and I'm not a physical scientist, but it's the sort of grittiness of the coal. If you have an extremely hard, lumpy bit in your coal, then that means that the grinder is going to bounce off that hardness. That's as hard as it can be. And so anything smaller than that hard bit of coal is not going to be ground like it used to be in the blend. So if you've got a sort of fine blend and you mix it with that sort of lumpier coal, then the lumpiness of the lumpy coal may stop the grinding happening in the finer coal, if that makes sense. Conversely, if you have hard lumps in your coal, then that actually might improve the grindability because it acts like a grinding agent itself. And so it's not easy to predict. And I probably didn't explain that well, but the complexity of how hard and how grindable is very variable, because some things are more grindable under certain conditions than others. And so it's not easy to generalize. That is the questions. I believe I have dealt with all of those. If I've missed any out, then feel free to email me and let me know. I've enjoyed talking to you. I hope you've enjoyed this, and I look forward to talking to you again in future. Thank you.